Hello friends, in the last lecture we learned about WKB approximation and used it to solve a problem on particle in a box having some finite potential inside the box. In this lecture we are going to continue our discussion on WKB approximation and apply it to solve a problem on quantum tunneling. In the last lecture, we have considered a case where energy of the particle is more than the potential barrier. In this lecture, we consider a case where energy of the particle is less than the potential barrier. Note that classically the particle is going to be reflected from this point because of the potential barrier. However, we know that a quantum particle can tunnel and penetrate in a region forbidden classically. We write the time-independent Schrödinger equation as minus h cross square by 2m d2 psi dx square plus v times psi is equals to e times psi. And then we just rearrange the equation as d2 psi dx square is equals to 2m v minus e divided by h cross square psi, and we write it as q square by h bar square times psi, where q is given by square root of 2m v minus e. And the solution of this equation is given by psi of x is equals to a times e power plus minus qx divided by h bar, and we just write qx by h bar equal to gamma, such that the solution is a e power plus minus gamma. Note that since q is real, the wave function is exponential with fixed q and a. And as we have already learned, the wave function is given by psi of x is equals to a plus minus gamma, and gamma is equals to 1 by h bar q times x. Now, this is for the case of a constant potential. What happens if v is not a constant and varies slowly in space? That is, v is a function of x. This is what we are going to learn in the next slide. Since the potential energy is varying slowly in space, q is not a constant, but this also varies slowly in space. Momentum is defined as square root of difference between total energy and potential energy. That is, momentum P is equals to square root of 2m E minus P. In this case, we have V is greater than E. Thus, P is imaginary. Thus, we can correlate Q with some imaginary momentum such that the magnitude of the imaginary momentum is equal to q of x. Similar to the case of constant q, WKB approximation tells us that we still get an exponential wave function. Psi of x is equals to ax times e power plus minus gamma of x. But now both a and gamma changes slowly with x. Gamma is given by the integral of q, and a of x is equals to c divided by square root of q of x. Probability of finding the particle in space is given by mod of psi x square is equals to c square divided by qx. Thus, probability of finding a particle at a point is inversely proportional to q of x. Before proceeding further, let me show the case of constant and slowly varying potential side by side. Time independent Schrodinger equation is given by d2 psi dx square is equals to q square by h bar square times psi, where q square is greater than 0. Q is constant in case of a constant potential and it varies slowly in space. Wave function psi x is exponential in both the cases and it is a real function. However, in case of a slowly varying potential, a of x also varies slowly in space and given by c divided by square root of q of x. And gamma of x can be obtained by integrating q of x. Now, let us go back to the tunneling problem and we solve it using WKB approximation. We have a potential barrier from x equal to 0 to x equal to a, shown by the blue line. Note that it is not a constant but changes continuously in space. Potential energy is 0 in the left hand side and in the right hand side of the barrier. Wave function is oscillatory in the left hand side of the barrier. The incident wave is traveling from the left to the right and the reflected wave is traveling from the right to the left. And the reflection is taking place because of the potential barrier. Wave function is oscillatory in the right hand side of the barrier also. And in this case, the transmitted wave is traveling from the left to the right. The transmitted wave has smaller amplitude compared to the incident wave. For example, you see here the incident wave has a very large amplitude, whereas the transmitted wave has a relatively smaller amplitude. We have to find the ratio of the amplitude of the transmitted and incident wave, which gives us the transmission coefficient. Inside the barrier, the wave function is exponential, and using WKB approximation, we can write it as c divided by square root of qx e power gamma of x plus d divided by square root of qx e power minus gamma of x. Gamma of x can be calculated from the integral of the q, and q is defined as square root of 2m v of x minus e. If a is very large, we can approximate psi of 2x as d divided by square root of qx times e power minus gamma of x. That means we drop the first term. In the limit a going to infinity, this is the exact solution, because in this case, e power gamma of x blows up at x goes to infinity. So we have to make c is equals to 0 such that the first part is 0 and we are left only with the second part. The same approximation works if v of x is much larger than the value of the energy. Thus, left of the barrier, we know the exact wave function given by psi 1 of x is equals to a e power I px by h bar plus b e power minus I px by h bar. Similarly, in the right of the barrier, we know the wave function exactly. Psi 3 of x is equals to f e power I px by h bar. Since b is equals to 0, p is equal to momentum and given by square root of 2me. Inside the barrier, we write the wave function using WKB approximation, and in the limit of large A, the wave function is psi 2 of x is equals to d by square root of q times e power minus gamma of x. Gamma is given by the integral of q. Now, let us try to find psi 2 at x equal to 0 and at x equal to a. So to get psi 2 at x equal to 0, we have to evaluate this integral. Gamma of 0 is equals to 1 by h bar integral 0 to 0 q of x dashed dx dashed. And you see that in this case, since the upper limit of the integral is equals to 0, gamma of 0 has to be equal to 0. In that case, psi 2 of 0 is equals to d divided by square root of q0. And at x equal to a, we have gamma of a is equals to 1 by h bar. And in this case, the upper limit of the integral is a q x dashed dx dashed. And thus, psi 2 of a is equals to d divided by square root of qa e power minus gamma of a. Now, the wave function decreases in the classically forbidden region, and the decrease of psi 2 from the left to the right is given by psi 2a divided by psi 2 0. And this is equal to square root of q0 by qa times e power minus gamma of a. By calculating the decrease of psi 2 in the non-classical region, we get the relative amplitude of the incident and transmitted wave. That is, mod of f divided by mod of a is given by the decrease of psi 2 in the non-classical region. Note that if we have a constant potential, in that case, the ratio of q0 divided by q of a is equals to 1. Now, in case of a slowly varying potential also, we can just approximate q0 by qa to be a number which is of the order of 1, and we can ignore it. Thus, relative amplitude of incident and transmitted wave is given by e power minus gamma of a. Now, if we take a square of this, that gives us the transmission coefficient. Note that gamma a can be calculated by integrating q of x, where q of x is given by square root of 2m b minus e. Note that for a constant potential, gamma is just 1 by h bar times a times q. And thus, for a constant potential, P is equal to e power minus 2 by h bar times a times q. And we can put the value of q in this equation, and we can rewrite the transmission coefficient in this form. Thus, we find that the transmission coefficient P decreases exponentially with increasing A and oblique or with increasing V. Let us take a case where V of x is inversely proportional to x, as shown here. Now, the quantum particle hits the barrier at x equal to 0, and then it exits the barrier at x equal to a. Distance that the particle needs to cross before it can escape the potential barrier depends on the energy. Thus, the width of the barrier is not fixed, but it depends on the value of energy E. Lower the energy of the incident wave, higher is the width of the barrier. For example, in this case, for the orange line, the energy is minimum and width of the potential barrier A is maximum. On the other hand, for the red line, the energy is maximum and width of the potential barrier is minimum. Since transmission coefficient decays exponentially with the barrier width, incident waves with lower energy has less transmission coefficient. Let us write a code to calculate this. Let me first explain the code. The potential is taken to be 1 divided by 1 plus x. The incident wave hits the barrier at x equal to 0 and escapes at x equal to a. Now, value of a depends on the value of energy of the incident wave. Now, at the point where it escapes the potential barrier, the value of energy is equals to value of the potential energy. Thus, in this equation, if we just put E is equals to 1 by 1 plus A, and then from this, we can estimate the value of A. This is done in this step here. Then we need to find the transmission coefficient. Transmission coefficient is given by e power minus 2 times gamma of A, where gamma of A is given by the integral of Q. In the code, we define Q here, and then the numerical integral to calculate gamma of A is done over here. And finally, the user-defined function that calculates the value of gamma returns the value of gamma. In this step, the transmission coefficient is calculated using a for loop. We are using a for loop because we want to calculate the transmission coefficient for different values of energy. And the energy value is varied from 0.01 to 0.1. We call the function to calculate gamma in this step, and using that value, we are calculating the value of the transmission coefficient for different values of energy. Finally, we plot the results in this step. Let us take a closer look at the code and then run it to generate the plot of transmission coefficient as a function of energy of the incident wave. This is where we define the energy range for the incident wave varying between 0.01 to 0.1. Then we have one user-defined function to calculate gamma. First, we find the width of the potential in this step. Then we define the potential function V. Then we define the function Q. And finally, we integrate Q to get the value of gamma. The function returns the value of gamma for some given energy. Here we have a for loop which calls the user-defined function to calculate gamma and find the transmission coefficient for different energy of incident wave. Finally, we plot the transmission coefficient as a function of the energy. Let us run the code. This is the plot of transmission coefficient as a function of energy generated by our code. Note that both x and y axis is in log scale. Energy of the incident wave changes just by one order of magnitude. However, the transmission coefficient changes by almost 14 orders of magnitude. The type of potential we have chosen for our code is very similar to what we get in case of Gamow's theory of alpha decay. In case of alpha decay, the parent nucleus X emits an alpha particle and it is converted to some other nucleus Y. Before the decay, the alpha particle moves to and fro inside the nucleus, and energy of the alpha particle is E, as shown in this diagram. Strong nuclear binding prevents the particle from escaping the nucleus. A finite square well potential is the simplest possible model for nuclear binding. The finite barrier, which is typically having a height of more than twice the energy of the alpha particle, prevents the alpha particle from escaping the nucleus. Note that we cannot take some infinite square well potential because in that case the alpha particle will never be able to escape. To escape, the alpha particle must tunnel through the barrier. Once far enough from the nucleus, Coulomb repulsion by remaining nuclear charges pushes it further away and the alpha particle finally escapes. If we assume the square well potential barrier is at R1, the particle has to tunnel all the way to R2, and then we see that the Coulomb repulsion will push it further away. Note that the Coulomb repulsion is repulsive because the alpha particle is positively charged and the remaining nucleus is also positively charged. Note the similarity of potential profile shown by the red line in this picture between Gamow's theory of alpha decay and what we did with the code for tunneling through potential barrier. Geiger-Newton law relates the lifetime of the parent nucleus with the energy of the emitted alpha particle, which can be experimentally measured. The relation is log of lifetime is equals to A divided by square root of E alpha plus B, where E alpha is the energy of the alpha particle. Thus, one can estimate the lifetime of parent nucleus from energy of the emitted alpha particle. For example, for uranium-238, the energy of the emitted alpha particle is 4.27 MeV, where 1 MeV is equals to 10 power 6 electron volt. On the other hand, for polonium-212, the E alpha is 8.95 MeV. Note that the half-life for uranium is 6 into 10 power 9 years. On the other hand, half-life for polonium is 0.5 microsecond. Note that although the energy of the emitted alpha particle varies only by a factor of 2, lifetime varies by several orders of magnitude. Remember that alpha particle is emitted from the parent nucleus X, which is converted to some other nucleus Y. Let us try to estimate the lifetime of parent nucleus using Gamow's theory. Let Z times E be the charge of remaining nucleus Y after the alpha particle escapes the parent nucleus. Charge of the alpha particle is 2E. Thus, once the particle travels from R1 to R2, it is free from the nuclear binding, and Coulomb repulsion by the remaining nuclear charge pushes the particle further away. The Coulomb repulsion is given by 1 by 4 pi epsilon naught Ze, where Ze is the charge of the remaining nucleus, and 2E is the charge of the alpha particle divided by R. Applying WKB approximation, we can find the transmission probability T, which is equal to e power minus 2 gamma, where gamma is calculated from this integral. In the integral, the lower limit R1 is the radius of the parent nucleus X, which is of the order of 10 Fermi, where 1 Fermi is 10 power minus 15 meter. The point at which the particle finally escapes, the energy of the particle should be equal to the potential energy. That is, at this point, the potential energy is equal to the energy of the particle. Thus, R2, the upper limit of this integral, can be obtained by equating E with the Coulomb repulsion. Then gamma can be written as this integral square root of 2me by h bar integral R1 to R2 square root of R2 by R minus 1 dr. Generally, R1 is much smaller than R2, and in that case, gamma can be approximately written as K1 times Z divided by square root of E minus K2 times square root of Z R1, where K1 and K2 are constants. If V is the velocity of the alpha particle, time between two collisions with the wall is given by 2R1 divided by V, where R1 is the radius of the nucleus. Inverse of this quantity is the collision frequency, which is equal to V by 2R1. Probability of alpha emission per unit time is a product of collision frequency and transmission probability given by V divided by 2R1 times e power minus 2 gamma, where e power minus 2 gamma is the transmission probability. Lifetime of the parent nucleus is inversely proportional to the probability of the alpha emission. Thus, we can write half-life tau half is equals to 2R1 divided by V times e power 2 gamma. Taking log on both the sides, we get log of tau is equals to 4R1 divided by V times gamma. Now, replacing the value of gamma from this equation, we can write log of tau is equals to 4R1 K1Z divided by V times 1 by square root of E minus some term which is not a function of energy. Thus, Gamow's theory of alpha decay indeed captures the Geiger-Newton law. Let us see whether our code can qualitatively capture Geiger-Newton law. Our potential profile looks very similar to what is used in Gamow's theory. The vertical line shows the finite potential wall. Then we have a potential which is decaying continuously in space. This is qualitatively similar to Coulomb repulsion. We increase the energy of the alpha particle from low to high and calculate the transmission coefficient. The transmission coefficient is inversely proportional to the lifetime tau. Now, according to Geiger-Newton law, if we plot log of tau as a function of 1 by square root of E alpha, where E alpha is the energy of the alpha particle, then we should get a straight line. Let us plot log of T inverse as a function of 1 by square root of E. If we get a straight line, that will indicate that our model is good enough to capture the Geiger-Newton law. Let us run the code and plot log of T inverse as a function of 1 by square root of E. Thus, plotting log of T inverse versus 1 by square root of E, we get a nice straight line as shown here. Thus, our simple model captures the Geiger-Newton law qualitatively.